Structured exception handling is a feature that found in Microsoft Windows operating system for handling exceptional conditions that may occur during the execution of a running process. The exceptional condition may be caused by error related to hardware such as illegally accessing protected memory location or software related such as attempting to write a file that is only read only using SEH. A process can be notified of the occurrences of such as error that allowing the process to recover from the specific exceptional condition and return to normal operation. So if you look through the some visual C++ code and notice the keyword like try and accept, leave, finally, and the API call raise exception. As you are seeing the code that is using structured exception handling and realize it SEH was not designed specifically for Microsoft C++ and it can be used by any programming language supporting in the Windows environment. The control structure used by SEH is located in the stack of each thread in a process in Windows, as every stack frame contained a block of structured exception and handling information inside the SEH. Inside the SEH block is a tuple list of memory address called exception and registration record. This is the one record for exception handler register for use in the function, and for each record contains a memory address that points to the next record. So in this list linking the record in this way makes it possible for the operating system to run programmatically and move through the record list when searching for the proper index handler, a second memory and a address point to the code. In an exception handler that is used to handle the specific exceptional condition, if the function does not use structure exceptional handling, then only the exception registration record for the default such as exception handler will be present in the SEH block in the feature stack frame. The presence of Windows structured exception handling allows buffer overflow and exploit authors to solve some of the problems they face. First, how do you execute your exploit code after you have injected it into the buffer? Next, do you keep the process from the crashing if your export code accidentally attempts to access an invalid memory location? In some cases, these problems can be overcome by using Windows' own structure exception handling mechanism. Let's look at the history of example at how Windows structure exception handling was used to do. Just this possible of the most famous example of the structure exception handling exploit was used by the code red worm released on the internet in July of 2001, and the code red exploited a buffer overflow vulnerability found in the component of the indexing service used by Microsoft web server. Internet Information Server. This exploit allowed the infected Microsoft server, then it spread other system with the same vulnerability, and this is the actual exploit code used by the code red in the middle, and this is the URL of the code that sends the web server using the HTTP just as an web browser can. In the word written SEH, the record which pointed to the exploit code to the stack. So code red ran its own exploit code using the normal Windows exception handling process. Very clever and very sneaky. Which is very clever and very sneaky. Before we finish with the module, we need to cover a type of overflow condition like these occur inside a process that is somewhat related to buffer overflow conditions. And the integer overflow are arithmetic error that occurs only when adding or multiplying two or more integer results in an integer value that is larger than the storage space and which is allocated to store the value, and such case an unexpected unexpected integer value results. If this incorrect value is not detected and corrected, it can cause a problem in the running program, including buffer overflows. Let's take a look at the couple of simple and impractical examples of integer overflow. In C code, an unsigned character variable can store in 8-bit an integer value in the range of 0 to 255. So if we declare an unsigned character variable and assigned a value of 255 and add a 1 to the value, then assign the result to another unsigned character variable, so what will be the value of the result? The result will be 0, not 256, because the assignment of a value too large for the result variable to store causes an integer overflow. So you can say the variables or odometer flip back to 0, and integer overflow work in the opposite direction too. When attempting to store an integer value, this is too small for a variable data type. A signed character variable can store an 8-bit integer value in the range of negative 128 to positive 127. If we declare a signed character variable and assign a value of negative 128 and subtract 1 from the value and assign the result to another signed character variable, then what will be the value of the result? So the result will be 127, not negative 129, because the assignment of a value too small for the result variable to store, so it causes an integer overflow. So as you can see, the overflow the variable, the odometer advance all the way to back to the all 9 just in a wild flip. Integer overflow finally conditions are normal part of the arithmetic operation in computer program. It is a responsibility of the program to write code to recognize when an integer overflow occurs in handle them and appropriately for the situation when an integer overflow condition is not caught and corrected, and for that reason the resulting overflow value is used to control memory allocation or decision of a program logic. Bad things can result, such as buffer overflows and other types of memory and access errors that can crash a program or create an exploitable vulnerability. As a user of a or as a user or like a system administrator, all you can do is to keep the minimal necessary software installed on your system and always patch what your software you want to keep.